In the event that we have a non-homogeneous differential equation that has an input function that's not of the type that we saw in the previous set of lessons, we use a technique called variation of parameters. It's based on the idea that we have a fundamental set of solutions, and for a second order differential equation, we would say we have a y1 and a y2. And then the particular solution takes on the form u1y1 plus u2y2, where u1 and u2 are unknown functions of x. In this lesson, we're still considering linear differential equations that have constant coefficients. That said, we're going to develop this a little bit more generally than that. Starting with the differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x y equals g of x, where now the right-hand side is of something more interesting than what we saw before. So it could be a natural log or a tangent or an inverse tangent or that sort of thing. Standard form is obtained by dividing by the coefficient function of y double prime, and we have y double prime plus p of x y prime plus q of x y is equal to f of x. Then, as we've done before, we're going to write down the form of the particular solution. In this case, yp is equal to u1 y1 plus u2 y2, where all the u's and all the y's are understood to be functions of x. And I'll let you know, I would never ask you to show me this process. We're going to lead to a result, and it's the result that you're going to need to know. But I'm going to develop this so you see where it comes from. Yp prime is u1 prime y1 plus u1 y1 prime, using the product rule, likewise, plus u2 prime y2 plus u2 y2 prime. You can verify that yp double prime is going to be u1 double prime y1 plus 2u1 prime y1 prime plus u1 y1 double prime plus u2 double prime y2 plus 2u2 prime y2 prime plus u2 y2 double prime. Substituting that into the differential equation gives us, let's face it, a lot of terms. Let's focus on one particular set of terms. u1 y1 double prime plus p of x times u1 y1 prime plus q of x times u1 y1. Pulling those out of this, we get u1 times the quantity of y1 double prime plus p y1 prime plus q y1. The reason this matters is we said that y1 was one of the solutions to the homogeneous differential equation. Therefore, all of that is equal to 0. Likewise, u2 y2 double prime plus p u2 y2 prime plus q u2 y2 is also 0. So for bookkeeping purposes, I'm going to go ahead and get rid of these. And the equation that we're left with is u1 double prime y1. Now we have here a 2 u1 prime y1 prime. I'm actually going to write that down as u1 prime y1 prime plus itself. Moving forward, we have u2 double prime y2, and then I'll do the same thing with u2 prime y2 prime, writing it down 2 times instead of using the coefficient of 2, plus p of x times u1 prime y1 plus p of x u2 prime y2, whole thing equals f of x. Okay, I know this is a hot mess right now. I'm again going to single out some terms. If we look just at u1 double prime y1 plus u1 prime y1 prime, and if you take just a moment, I'm sure you can convince yourself that this is actually the derivative of u1 prime times y1. Furthermore, we have here this u2 double prime y2, there shouldn't be a plus there, plus u2 prime y2 prime. that also equals a derivative of u2 prime this time times y2. So putting those together, the squiggly underlines actually can be written as the derivative with respect to x of u1 prime y1 plus u2 prime y2, which is kind of interesting because we also have p of x times all that same stuff, u1 prime y1 plus u2 prime y2. And that leaves stuff that's not underlined over here, u1 prime y1 prime plus u2 prime y2 prime, and the right-hand side was, of course, f of x. I know, just hang on for just a bit. If we require that u1 prime y1 plus u2 prime y2 equals 0, then the derivative is 0, and p times that thing equals 0. And we end up with the result that what's left, u1 prime y1 prime plus u2 prime y2 prime is equal to f of x. I know, this is kind of funky. It's a big ol' if. Textbook authors at this level don't usually explain that. But understand that with this condition that u1 prime y1 plus u2 prime y2 equals 0, that leads to u1 prime y1 prime plus u2 prime y2 prime equals f of x. Okay, now I'm going to try to bring this all together here. u1 prime and u2 prime are the derivatives of the unknown functions u1 and y1 that started this whole conversation here. And what we have here is actually a system of equations where u1 prime and u2 prime are the unknowns. Now, if we consider a system of equations, ax plus by equals e and cx plus dy equals f, then the connection here is that x and y are the unknown variables, just like u1 prime and u2 prime are the unknown functions in the previous conversation. Then using something called Cramer's rule, if you need to, look it up, we find that x is equal to, I'm going to write this as dx over d, where d is a 2x2 determinant of the coefficients of x and y. So it's the 2x2 determinant of a, b, c, d. And to compute a 2x2 determinant, you may recall, upper left times lower right minus the product of lower left times upper right. So that's AD minus BC. Okay, great. dx is also a 2x2 determinant. And it's what happens when we take what we just looked at A, B, C, D, but replace the first column, those are the coefficients associated with the x variable, with the constants that we have on the right-hand side. And so instead of A, B, C, D, we have E, B, F, D. And it's again computed as like ED minus BF. And I don't want to get too far into like the rest of this, but I'll tell you that y, well, I guess this is the rest of it, is equal to dy over d, where d is the same as before, the coefficient determinant, and dy is equal to what we would get if we took d and replaced the second column, that's the one associated with y's, using this e and f, a, e, c, f. And of course, that's af minus ce. Again, if you want to like really research Cramer's rule, that's what you search for. But now I'm going to just connect that linear system of equations from algebra to this system of differential equations. And instead of A, B, C, and D, we have y1, y2, y1 prime, and y2 prime. So I'm just copying this down here. Let me get rid of the blue stuff. No, I'm going to leave the blue stuff. That's what we're solving for. We have a determinant that is the equivalent of this denominator determinant d, right? It's the determinant that we get from the coefficients of the unknowns. Here, the determinant that we get for the coefficients of the unknowns is y1, y2, and then y1 prime, y2 prime. You may remember this. It's something that we called before the Wronskian. I'm also going to write down two other determinants. W1 is equal to, it's just like the Wronskian, except this is basically the dx up here. We're going to replace the first column using what's on the right-hand side of these equations. And what we get from the right-hand side was, suppose u1 prime y1 plus u2 prime y2 is equal to 0. So we have a 0 up there. Then u1 prime y1 prime plus u2 prime y2 prime is equal to f of x. And so this is f of x. The second column is what the Wronskian second column was, y2 and y2 prime. And w2, you can probably guess what this is. The first column is y1 and y1 prime. The second column is 0 and f of x. Now, if you connect this to Cramer's rule, or just pick it up from here and believe me here, then we've been solving for u1 prime and u2 prime. According to Cramer's rule, u1 prime is w1 over w, and u2 prime is w2 over w. And both of these at this point are 2 by 2 determinants that we can get by multiplying upper left by lower right and subtracting lower left times upper right. This is u1 prime. That means that u1 is equal to the integral of w1 over w times dx, and u2 is equal to the integral of w2 over w times dx. Now, I said I wouldn't ask you to reproduce this process here. I won't. What you need to know is essentially on this page, I need you to know what the Wronskian is, what W1 is, what W2 is, what U1 and U2 are. When we form W1 and W2, I need you to remember that f of x is what you get on the right-hand side after the equation is in standard form. And then finally, we said that the particular solution has the form yp equals u1 y1 plus u2 y2, where y1 and y2 were the solutions to the homogeneous differential equation.